So this is the 2024 Higher Level Maths Leaving Cert Deferred Paper 2, question 7A1. Fiach owns a forest. The heights of the trees in a forest of this type are usually normally distributed with the mean height of 360 centimeters and the standard deviation of 27 centimeters. Use this information to answer parts A1, A2 and B. One tree is picked at random from this forest. Find the probability that the height of this tree is between 330 centimeters and 390 centimeters. Okay, so let's write down what we know first. We know that the mean is 360 centimeters and the population standard deviation is 27 centimeters. We're going to use this formula here to work out the z values that we need. So let's write down the question that we're asked. We are asked to find the probability that the height of this tree is between, so we're going to call it x, is between 330 centimeters and 390 centimeters. What we've got to do is change these two values here into a z value using this formula. So we have to find the probability that z is greater than 330 minus 360 divided by 27 and 390 minus 360 divided by 27. So these two z values are, if we take z here in the middle again, we have 1.11 here, minus 1.11 in fact, and 1.11 out here as well. Now this one is repeated here, so I've just rounded it to 2 decimal places because I know that's what our tables can read. So let's deal with this. Now we have the probability that z is greater than minus 1.1, less than plus 1.1. Let's just draw that out on our standard normal distribution. So we have 0 in the middle, we've got 1, 2, 3 here, standard deviations from the mean, minus 1, minus 2, minus 3 standard deviations from the mean here. So the area that we're looking for here is between minus 1.1, which is about here, and plus 1.1, which is about here. So we're looking for this area here in the middle. It's symmetrical, although it doesn't quite look symmetrical here, but it is symmetrical. So we are looking for this area in the middle here. How do we work out the probability of the tree's height being in this area? Well, what we're going to do is we're going to find the probability of being in this part of the graph down here. We're going to find the probability of being in this part of the graph down here and subtract the two. So it's going to be the one further right minus the one further left. So we have the probability that z is less than plus 1.11 minus the probability that z is less than minus 1.11. That's what we need to work out. If we subtract those two, that'll give us the area in the middle. So this one here we can read from our tables. It's easy enough to read. We have less than and we have plus 1.11 here. So we can read that. I'll just write it out for the moment again. I'll look it up in a few minutes. So what about this one here? The problem with this one here is that we have a negative 1.11 here. We can't look up minus 1.11. We can look up plus 1.11. This is less than, so that's fine. So let's just see how we would work this one out. Let's take our standard normal curve again and look at minus 1.11 here. We want z to be less than minus 1.11. So we're looking for this area down here. We can't look up negative 1.11. So let's look at positive 1.11. This area here is the same area as this area here. So this area is the same as this area here. So if we could work out probability of appearing in this part of the graph, it's exactly the same as the probability of appearing in this part of the graph here. Now we can look up 1.11 in our tables. But the problem with that is it'll give us the probability of being down in this part of the graph here. So what we've got to do is subtract that from 1 to give us the area that we're looking for, this area here. So let's do that. So I'll just put this in a bigger bracket here. We need 1 minus the probability that z is less than plus 1.11. Okay, so now let's just take away this big square bracket here. We've got probability of z is less than 1.11 minus 1 plus probability z is less than 1.11. Now if you notice here, we've got the probability z is less than 1.11. We've got the probability z is less than 1.11. That's two of them. So we've got 2 times the probability that Z is less than 1.11, and then we have this -1 here as well. So now really we've reduced our problem down to this. So let's look up our Z is less than 1.11. If you do that, you get a value of 0.8665. So if we work that out, it's just calculator work after that, we get 0.7330. That just means that the probability of picking a tree at random from Fiach's forest, that it is between 330 centimeters in height and 390 centimeters, in other words that it appears in this part of the graph here, is 0.7330, or 73.3% chance that that will happen. Okay, so this is part 2. The shortest or smallest 5% of the trees in the forest are not sent to the factory when the forest is harvested, as they are not tall enough. What is the minimum height that a tree needs to be in order for it to be sent to the factory when the forest is harvested? So what I've done here is I've just drawn a standard normal curve. So this is the Z value that we're going to be looking for in this question here. It's negative because we're looking at the bottom 5% of the graph. So I've also shaded in the top 5% because this Z value here will be the same as this Z value here, but this Z value will be negative, this one will be positive. So we are actually going to end up looking for this Z value up here because we can't find negative Z values in our tables. So let's write down what we're given anyway. So we have the probability of Z being less than X, which is the height of our smallest tree, minus the mean, which is 360, divided by 27, and we want that to be less than 5%. So 0.05. So this Z value here is going to be negative, it's down here, but we can't look up negative Z values in our tables. So we're going to look at this positive version of the same Z value. But the 5% that we're looking for is to the right of it, it's up here. Again, we can't look up greater than, we can look up less than particular Z values. But less than this particular Z value will be 95%. Down along here is 95% of the graph. So really I can change this inequality to Z less than X minus 360 over 27 being less than 0.95. This Z value here is now positive and it's here. So let's look for a probability of 95% or 0.95 in our tables. So if we look at our tables here, 0.95 is here. You've got 0.9495 and you've got 0.9505. Either one of these will be acceptable. I'm going to go for the one on the left hand side, which will give me a Z value of 1.64. You can also look at the probability halfway between these two probabilities, which is probably closer to 0.095 anyway. So you could talk about a Z value of 1.645. They'll all be acceptable, all three will be acceptable. But I'm going to look at 1.64, which has a probability of 0.9495 or rounded to 0.95. So 1.64 is what I'm going to use. So in other words, the X minus 360 divided by 27, that Z value is actually 1.64 on this side of the graph. However, our Z value, the one that we actually need, is this one down here. We actually need minus 1.64. So all we've really got to do is solve this for X. So what you need to do is multiply both sides by 27 and then add 360. That will give you an X value or a tree height of 315.72 centimeters. So trees smaller than this will not be sent to the factory. If you used minus 1.65 or minus 1.645, I'll just give you those heights. They're almost the same as this one anyway. 1.65 would give 315.45 centimeters, and minus 1.645 would give you 315.585 centimeters. All three should be acceptable in the exam. Okay, this is part B. Fiach claims that the mean height of the trees in her forest is different to the usual height because they have become infected with a disease. She picks 100 trees at random from her forest and measures their height. The mean height of this sample is 350 centimeters. Test the hypothesis at a 5% level of significance that the mean height of the trees in the forest is different to the usual height of 360 centimeters. The null hypothesis is given below. State your alternative hypothesis, state your conclusion, and give a reason for your conclusion. So the null hypothesis is that the mean height of the trees in Phoenix forest is 360 centimeters. So that's already given. Our alternative hypothesis then is, let's say H1, that the mean height of the trees is different to 360 centimeters, or the mean is not equal to 360 centimeters. That's our alternative hypothesis H1. So let's do these calculations then. So we're told that the sample n is 100, that the mean of our sample is 350 centimeters. The mean that's been claimed is 360 centimeters, and our standard deviation is 27 centimeters. So we're going to work out our test statistic, which is z, which is just x bar minus mu over sigma over the square root of n. So in our case, x bar is 350. We've got to subtract 360, divide by sigma, which is 27, divided by the square root of 100. So that is just calculator work. You can do that no problem on your calculator, and you should get a value of minus 3.7037 and so on. So quite a low Z value. So now we need to write out, it says here, state your alternative hypothesis, state your conclusion, and give a reason for your conclusion. So we need a conclusion first. Conclusion is that we're going to reject the null hypothesis, that the mean height of the trees is 360 centimeters. So the reason for that is that the modulus of our Z, our test statistic, is greater than 1.96, or you could say minus 3.7037 is less than minus 1.96. So the test statistic is in the critical region. That's it. Okay, let's look at part C. Fiach wants to estimate the number of trees that have become infected with the disease. She picks a random sample of 160 trees and examines them. 48 of these trees are infected with the disease. Find the 95% confidence interval for the proportion of trees in the forest that are infected. Give each value in your answer correct to 3 significant figures. So this is a confidence interval for the proportion. We have sample size of 160, and we have a p hat then as 48 over 160. So we want a confidence interval for the proportion. So that means the actual population proportion is going to be between our p hat, which is 48 over 160, minus our margin of error, and 48 over 160 plus our margin of error. Our margin of error is 1.96 times the square root of p hat, which is 48 over 160, times 1 minus p hat, which is 48 over 160, all divided by n, which is 160. Do the same on the other side, so it's plus 1.96 times the square root of p hat, 48 over 160, times 1 minus 48 over 160, divided by 160. So that's really our confidence interval. We've just got to do these calculations. So we have p greater than and p less than. This is all just calculator work. So when you do all of this on your calculator, you get 0.22899 and so on. And then on the right hand side you get 0.371007. So we've got to round these to 3 significant figures. Give each answer correct to 3 significant figures. So 3 significant figures would mean we would stop there. So that's 0.229, and we need to stop here as well, so it would be 0.371. Remember, you don't count leading zeros. Okay, and that is it. That's our confidence interval for the proportion. So in part 2, it says explain what this 95% confidence interval means in the context of the question. So I've written out my answer here. It just says that if the process was to be repeated 100 times, you would expect that the actual population proportion would be within 95 of them. Okay, so this is part D. The diagram below shows a normal curve with a mean of 360. On the same diagram, draw a new curve that will have the same standard deviation as the curve, but with the mean of 350. Use the same axis and scales. So all you've really got to do is just shift this curve down to the left here, so that the new mean here would be 350. So the mean here would be 350. The mean here is 360. So mine's a little bit shaky there. Hopefully you guys will be able to do it a little bit smoother than that. But you're just shifting the graph 10 units to the left. In part 2, it says the diagram below shows the same normal curve as above with a mean of 360. On the diagram below, draw a new curve that will also have a mean of 360, but that will have a smaller standard deviation than the curve given. Use the same axis and scale. So I've done that here as well. All you would have to do is bring these two tails in so that this new curve will have a smaller standard deviation than the original curve. It would have a smaller spread, in other words. Okay, and that's it for this question.